giving a talk about conformal invariant measure on Jordan curves.
Okay, thank you. Thank you for giving me the opportunity to speak here today. So this is a joint work with Guillaume Baverez, who is in Beijing at the moment. Right, so I wanted to give a little bit of motivation, but actually I'm not sure this is really necessary now after the talk of Evelina. But okay, so still let me describe slightly the type of curves we are interested in. Let's say you have your favorite models from statistical mechanics. So this could be, for instance, the Ising model. So there is a phase transition in the Ising model if you are in dimension. So here I'm drawing a domain like this, and I put boundary conditions. So on the left-hand side of the domain, I prescribe my spins to be plus. On the right portion of the domain, everything is minus. And if the temperature of the model is subcritical, so small enough, then these boundary conditions will have a big impact. Basically, I will have a straight line here where everything will be, most spins will be pluses here, and most spins will be minuses here. Whereas if the temperature is large enough, everything will be noisy. It will be, a cloud of pluses and minuses. And there is a critical temperature where you have a mixture of both pluses and minuses, and actually you have some sort of fractal curves like this that separates the spins. Okay, and so we are interested in this kind of models, and Polyakov understood. Should not move this actually. So Polyakov, in the 70s, understood that at criticality, in the scaling limit, this type of models exhibit conformal invariance. And so, okay, so what does it mean, conformal invariance? So for instance, if you are looking at a spin-spin correlation, you have a function of two variables that will enjoy symmetries, conformal symmetries. But also this type of curves here that appear in the limit will also enjoy symmetries, the same way as, let's say, Brownian motion in dimension 2. Or, Brownian motion is conformal invariant, and indeed, Brownian motion is also the scaling limit of some statistical mechanics models, simple random walk. Okay, so today, the purpose of my talk is to study the goal, if you want. Study random curves, random Jordan curves actually. This type of curves here. And okay, let me recall that the Jordan curve is just a simple root. That's a Jordan curve. So here I was in a slightly different setting. I was in a chordal case. I will be considering the loop case. Okay. And so I'm going to give you the plan of the talk now. So this talk will be about three approaches. To defining conformally invariant measures on Jordan curve. So the first approach, I think you have already seen it this morning. Again, I believe I saw it on the board. The first approach is by Schramm. Which is based on the restriction of the domain Markov property. The second approach will be Kontsevich to have measures, which is based this time on the conformal restriction property. The third approach by Hero and Maillevin which is the unitarizing, based on the unitarizing property. So if you want, I'm going to describe the same object 3 times using different approaches each time. And these different definitions or characterizations of the same object will be very useful because they give different perspectives, on the same. Do I write big enough or? Yeah. So in each case, there will be mainly 2 steps. So the first one is more axiomatic, if you want, where we will give, we want a list of desired properties. And the second step will be more constructive. We want to build a measure that satisfies build a measure. So I'm for the non-probabilistic people, building a measure. It just means I want to build, I want to construct the random object I'm talking about. Right, and the punchline, if you want, the theorem that we have with Guillaume is that all these approaches are equivalent. Okay. Is the main message of my presentation clear? Or? Okay, so the first one, SLE. So SLE is very classical now, and okay, but let me still highlight the main properties. So here we will have a curve eta from 0 to infinity in the upper half plane. So here it's really the caudal case that I drew here. So I will have the random curve from one boundary point to another boundary point in a domain, and here I will be in the upper half plane. Since I'm talking about conformal invariant objects, I just need to describe what happens in the upper half plane, if you want, and then I will have it for every simply connected domain. So the axioms that we want are as follows. So axiom 1, we want scale invariant. For every lambda positive, I want lambda eta to be equal in law to eta. So the only conformal map that fixes 0 and infinity and that sends the upper half plane to the upper half plane are scalings. So that's why I'm asking this scaling invariance here. And the second axiom, axiom 2, is the domain Markov property. So what it says is that, let's say, so here, this is my upper plane, this is 0. And I run slightly the curve from up to time t. This would be eta of t. And I want to know what's the law of the remaining part of my curve. And one way of continuing the curve is I'm going to conformally map my slit domain. So I will take a conformal map that sends h minus the beginning of the curve back to the upper half plane. So if you want, this map does something like this, you know, now the curve is there. And I will run an SLE from 0 to infinity in that portion here. And if I map this back here, the point is that the object I get on the left-hand side has the same law as the whole curve. So that's the domain Markov property. And the result, so these are the two axioms, and if you want now the result by Schramm theorem, so that's Schramm 2000, is that there exists a unique family of continuously growing curves. So this family, so it's a family indexed by kappa. Which satisfy, so satisfying axioms 1 and 2. So that's a complete characterization of SLE if you want. So actually not quite complete because there is still, there is this parameter kappa that is not identified in this procedure. And kappa is related to the central charge. So for each value of kappa corresponds to a different central charge. If I modify kappa, modifying kappa basically means that I modify my model. So for instance, easing was corresponding to kappa equals 3. Okay, and so how do you construct the construction of this thing? So I'm not going to give you the construction, but the construction is explicit. So there is this general theory. So there is this Loewner theory. Which associates to each driving function a curve, or more generally a family of growing curves. And the case of SLE corresponds to taking the driving function equals to square root of kappa times the standard 1D running motion. Right. So if you have a function from R plus to R, then you can associate to it a curve or actually a hull. So this kind of growing objects in the upper half plane. And SLE corresponds to taking a random function, because SLE is a random. The function you take is a one-dimensional Brownian motion. Okay. So this is all very classical. And this gives, so for instance, this is a very like this this link with the Brownian motion is, of course, very powerful. Now we can apply techniques from stochastic analysis to make computations related to SLE. So, for instance, the most basic tool is Ito's formula. Okay. So this defines, if you want, random curves from 0 to infinity in H. As I said, using a conformal map, you can define it in any domain now. And there are many generalizations of the subject. And the generalization that will be useful for us, or generalization, if you want a different setup, is what's called the SLE, so SLE kappa loop measure. So this was introduced by Jan, 21. And instead of having a random curve, we will have a random Jordan curve. And this is not, before I was talking about the probability measure, because I had really the law of my SLE was a probability measure. Now this thing, this is not a probability measure anymore. It's an infinite measure because of potentially small and large groups. So this is an infinite measure, but that's the measure we want to exist.
Which is not the conformal ensemble.
It's not conformal loop ensemble now. It's different, but it's related to conformal loop ensemble. So basically, it's basically the counting measure of conformal loop ensemble. So for instance, let's say I want to sample a specific loop which contains 0 in its interior, for instance. I can consider a nested conformal loop ensemble. So I will have many in this nested CLE, I will have many loops that contain 0 in its interior. And I take basically the counting measure on that, and this will give me the SLE loop measure. So it's closely related, but so CLE, you have many different loops, whereas here I have one loop. In a sense, CLE is more general; it contains more information. Okay, so now I will move on to the second part and describe a little bit what's the Kontsevich-Suhov measures. And maybe I should mention that in the current literature there is how to say that people tend to call these measures the MKS measures for Malyavan, Kontsevich, and Suhov measures. But I want to stress that actually it doesn't really make sense because the measure in point 2 and the measure in point 3 are different. They are defined on different spaces, if you want. So that's something that I want to talk about. So, point 2. Okay, so I first need to introduce a definition. So I will take. So I have two Jordan curves like this. I have eta1 here, eta2 here, and I define so you know the sphere minus these two curves is composed of three distinct connected components. Two of them are disks that I call D1 and D2, and the third one is an annular topology. And I define lambda star of eta1, eta2 to be the log of zeta regularized determinant of the Laplacian, Dirichlet Laplacians in the domain D1, domain D2, divided by domain which is the annulus. Laplacians with the Dirichlet boundary conditions. So you know this is a quantity, a geometric quantity. Right. If you come from a CFT perspective, I guess this is very natural because reweighting your model by power of the determinant of the Laplacian amounts to changing the central charge. This is basically what's going to happen here. So that's why we define this. And I will fix a central charge Cm less than 1, and I take a measure nu c hat. So this one is a measure. So what I'm doing here, I'm describing the axiomatic part of the two steps I was talking about. So I first pick a measure on Jordan curves, on the space of Jordan curves. And I'm going to give you the desired property I want for this measure. So in order to do so, I'm going to introduce a new measure, this time for D, a simply connected domain. I define new D eta, which is going to be basically the restriction of nu to the curves that remain in my domain D. But there is a twist that depends on the central charge, so Cn over 2, lambda star, eta, nu c hat. So, you know, I have my measure, nu c hat, I restrict it to D, and then I reweight it with this exponential. So, you know, the log, basically what I'm doing here, I'm taking the determinant of the Laplacian to Cm over T. And so the axiom that we want is the following. Definition. Let's conceive of 20. This is a Cm restriction measure if for every conformal map phi that sends D1 to T2, the measure nu D2 can be obtained by pushing forward the measure nu D1. So here what it means is that if I want to sample my curve in the domain D2, I can do two things. Either I do it directly in the domain D2, or first I do it in the domain D1, and then I use my conformal map phi to send it to D2. And these two ways of sampling the curve are equal. Is this definition okay? So that's the axiomatic part And so the conjecture by Kontsevich and Swap is that there exists a unique conjecture for every Cm less than 1. There exists a unique Cm restriction measure. Unique up to a global multiplicative constant. And so the existence has been settled for actually not so far. So the existence is follows from a long list of works. So Werner in 2008 treated the case where the central charge vanishes, where the central charge is 0. Then there is Benoit, the work of Benoit Dubeda that considers another value of the central charge. And then there is Kampainen, Werner, and finally Jan, 21. And so basically the outcome of this list of works is that now we call this the SLE kappa loop measure. So the SLE kappa loop measure is a Cm restriction measure where Cm, so Cm is related to kappa by this formula. Right. And maybe I should say, yeah, I should have said this before. I always consider the case where kappa, so in my talk, kappa is always between 0 and 4, which corresponds to simple curves. So when kappa is between 0 and 4, this value of Cm it goes from -infinity to 1.
Are you considering genus 0 only, or any surface?
Yes, so I'm only considering genus 0. But I believe if you consider the genus 0 case should also implies a higher genus.
But how do you define this anomaly in high genus?
I'm not sure. To be honest, we only consider the sphere case or simply connected domains. No, okay. Yeah. Indeed, if you have sorry?
Yeah, I just wanted to ask if I missed something. So I'm imagining genus 0.
Yeah, you can imagine genus 0, but I don't think this is a big restriction because already in the genus 0 case, you can look at annuli and say that and look at the restriction of your measure to curves that remain in these annuli, and compare this with what you would have on a more general surface. Okay.
Yeah. So yeah, hopefully.
I think it's not known if the factor that you get with the lambda star.
Yeah, if the partial function is finite or something.
Yeah.
Yeah, exactly. So it's
Yeah.
a little bit, yeah. But there's some other formula you can use, I think. So it's not a big deal.
Okay.
I think, but just wanted to, if you have some insight.
No.
Yeah.
No new insight.
Thanks.
Yeah, so the main theorem, so the theorem with Guillaume is that uniqueness holds. Uniqueness holds. So that's with Guillaume. I also would like to mention that there is a new proof of uniqueness by Sai and Gao in 25, which works when Cm is between 0 and 1. And I want to tell you a few words about the proof. And I will go slightly into this proof. And hopefully by the end, I will not prove everything, but this proof will help me transitioning to the third part of Hérault-Maillavin. So the sketch of the proof. That this conformal restriction property enables us to derive an integration by parts formula. And from this integration by parts formula, we are able to construct a family of orthogonal polynomials. Which characterize the measure. And what I want to do now is I want to explain to you what is this integration by parts formula that we have. Because this integration by parts formula will also be, if you want, the main axiom in this Hérault-Maillavin formalism. It will be a different integration by parts formula. And you know, from a CFT perspective, this integration by parts formula is very natural as well. What we do is that we have our system, and we want to perturb it with a local conformal map, and see what this perturbation does to our system. So to be able to do this perturbation, I need to introduce the notion of derivative in my space. So I'm going to introduce Lie derivative. And okay, so from now on, I will restrict to curves that remain that separate 0 to infinity. So this is the J0 infinity is the space of Jordan curves separating 0 and infinity. And okay, I consider my Lie for each. My Lie derivatives will be indexed by Laurent polynomial vector fields. So you take V Laurent polynomial vector field. So this means that, you know, so I might have a singularity at 0 or at infinity. And I consider associated to V, I have the flow. Phi t, which is indexed by small complex values of t, where phi 0 equal the identity, and dt of phi t equals the.
You mean it's holomorphic somewhere? It's converging. The series is converging.
Also, it's a finite sum.
It's a finite sum.
Yes, it's always a finite
It's a
sum.
polynomial.
It's polynomial.
Okay.
It's a polynomial in Z and 1 over Z.
Okay.
So, right. So, okay, let me give you the three most basic examples. I mean, when V of Z is equal to 1 Z or Z squared, the flow I have, phi t, will be actually Möbius. So I will really have a conformal maps. But the point is that if I take other values of this vector fields, I will have maps that are conformal away of neighborhoods of 0 and infinity. It might be otherwise conformal or holomorphic only only a way of 0 and infinity. Okay, so that's let me draw a picture. The picture I have is this is my Jordan curve eta, and I perturb slightly my curve eta by phi t of eta. So when t is small, this is a small perturbation of the curve eta. So I will have some functions that will be differentiable. So I'm going to introduce now a family of test functions. Test functions. They are defined as follows. So this is my curve eta. I have 0 here, infinity here, because you know eta separates the two. I take the unit disks and I consider the conformal map. Actually, I write it e to the cf. This is the unique conformal map that is normalized so that 0 is sent to 0, and its derivative at the origin is positive, and so this is parameterized by c. So f prime of 0 is equal to 1. C is all of this depends on eta. So we can view c eta and f eta as functions of eta. And my space, right, and so f eta in particular, I can expand it about 0, and I can write it as follows. So it's z1 plus the sum of the coefficient an z to the n. And again, an, the map that I really have a map that sends eta to a1 of eta. So this is a function of eta. My set of test functions will be the following. So I will take the space of this infinity functions. So this is for C. And then I will consider polynomials in my coefficients an. So we can treat polynomials in an bar. And again, an element of this space, if I pick an f in that space, so f in C, what it does is that f takes a Jordan curve eta in my space J0 infinity of curves that separate 0 and infinity, and it spits out a real number, so f of eta, or a complex number. That's what my space is. Finally, my derivatives. Now I'm going to write a statement about existence of derivatives for these test functions. So proposition, if you want. So let me pick C, Laurent polynomial vector field. Phi t is flow. So there exist endomorphisms LV and LV bar, which so these operators, they take any function in my family of test functions and they spit out a new test function, such that for all eta in J0 infinity and for all f test function, f of phi t eta equals f of eta plus t LV f of eta plus t bar LV bar f of eta plus little of t as t goes to 0. So I have defined differential operators, and I have shown that for a large class of functions, my functions are differential. Good. And you know, almost by constructions, moreover, LV and L bar B are two commuting representation of the bit algebra. So the bit algebra is the algebra of this Laurent polynomial vector. So what it means, so this is almost by construction, if you want, is that the commutator of LV LW is given by L, the V bracket of VW. So that's the commutator, and that's the V bracket of vector fields. Okay. So now I have the ingredients, all the ingredients needed in order to state this integration by parts formula. So take new, so new is any CM restriction measure which is restricted to J0 infinity. So CM restriction measures are measures on Jordan curves that live on the Riemann sphere with no restriction, and now we just put an indicator function that my Jordan curves separates 0 to infinity. And so the theorem, that we had with Guillaume, but I should mention that Gordina also proved this integration by parts formula. So for all V in for all Laurent polynomial vector field, I have and for all test functions. Okay. So the L2 of new adjoint of LV is well defined on the space C and equal to so let me look at my notes. So it's equal to minus LV bar plus Cm over 12, the Schwarzian derivative of f minus 1 paired with V minus the Schwarzian derivative of G minus 1 paired with V times identity, where, so you know, as before, so this is eta, that was the function f, and now I can see, so this is the function g. and this symbol here means the Schwarzenegger derivative. The point is that it is explicit. Okay. Do you have questions concerning this or? So, okay, we are very happy with this formula for several reasons, but one.
The pairing is you integrate on the circle? Or?
You integrate close to the curve, actually. And inside the curve for this one.
This is like a one form, so you need to integrate on the contour.
Yes, but I'm integrating on the. So for f, I would be integrating on the contour, which is close to eta and inside eta, and for g, it would be outside of eta. And of course, it doesn't. The only singularity you have here are either at 0 or at infinity. So if you change a bit your contour. Okay, so this formula is very useful because basically here is the starting point for proving the uniqueness of such a measure. But it's also nice because it gives a meaning to the following path integral. So path integral for SLE. D nu kappa, so I will write the dependence of kappa here, eta equals the exponential, I'm never sure about the constant, C over 24. Loewner energy of eta, D nu third of eta. So kappa equals 1/3 corresponds to the central charge equals 0. So this measure at the central charge equals 0 enjoys much more symmetry. It's basically invariant under local conformal transformations. So if you want, you kind of play the role of our favorite Haar measure or whatever. And we rewrite this measure by this term here, where this is the Loewner energy of the curve. This is also called the universal Liouville action. And I'm saying that this integration by parts formula gives a meaning to this path integral. Yes, okay. So obviously the problem with this is that for a curve eta that is sampled from this measure, this energy here will be infinite almost surely. So this expression doesn't make sense. But the point is that if you start from there and make formal computations, you will be able to derive an integration by parts formula for the measure of that form. And basically, the Schwarzenegger derivative of f-1 and g-1, they appear when you differentiate this.
Can you remind me the definition of the Loewner energy?
Yeah, so you integrate over d f prime over f prime prime over f prime. Yeah. That's the integral g prime prime over g prime. Yeah. There are pi's somewhere. 1 over pi. This 1 over pi. That's 4 log g prime infinity over f prime 0. Minus. Yeah. And so in a way, what's very nice is that this Loewner energy. So you see that the curve has to be quite smooth if you want this to be finite. And indeed, the curves for which this Loewner energy is finite are quite smooth. But the point is that when you differentiate this guy, you obtain such formulas here, which are much more regular because these guys, they are finite for any Jordan curves. So although this path integral doesn't make sense, the integration by parts formula you get does make sense. So how much time do I have now?
8 minutes.
8. Okay, so that's my transition to the third part, which is this Hérault-Maillard measure. And it's really the starting point of, I don't know if it's the starting point, but you want to define the axiom. The first axiom in this step, in their approach, is basically this. They want to write some sort of path integral formulation of their measure, but the path integral will not make sense, whereas the integration by parts formula you write does make sense. So that's. And also, I want to mention that here I have the appearance of the reference measure. Most of the time in these path integrals, the reference measure doesn't even make sense. But I want to emphasize that in this integration by parts formula, the reference measure has disappeared as well. So it's nice because the terms that were infinite are finite now, and the reference measure that possibly does not exist does not appear as well. So the point is that the integration by parts formula is very different because their differential operators are different. So I'm again drawing the same picture as usual. This is my curve eta, 0, infinity. And I have f here and g here. So f and g are actually continuous up to continuous and injective up to the boundary. So if I define, so I can define homomorphism of the circle h eta, so they depend on eta if you want, as g minus 1 composed with f restricted to the unit circle. So effectively what I do is that I pick a point here on my circle, I look at its image by f, maybe here, and then I take G to map it back to the circle. And this is my image of my point. So to each curve eta, I can associate what's called the welding homomorphism of the curve. And if you want the axiom 0 that you want a measure mu on the space of homomorphisms of S1, which satisfy the following path integral to d mu of h equals the constant. Exponential minus CL of 12, the energy of the curve associated to it, dh. Here, this h is the Haar measure on VO of S1, which of course does not exist. And so if you want, I take so how is it, this thing is defined by if there is a curve eta that welds the homomorphism H, then I define this Loewner energy to be the Loewner energy of the curve. And if it doesn't, I just I don't know, define it to be infinity. So again, this is not well defined, but what Hérault and Baverez did is they wrote a formalism for this in terms of integration by parts formula. So the definition, if you want. One. HCl unitarizing measure U is a measure satisfying the following integration by parts formula. So I want the adjoint of ln to be L minus n plus CL over 12 theta n times the identity on L2 of mu for all n. So here, okay, so I'm not going to write everything. This guy, there is a shortened derivative here. And this one, there are differential operators, so there are Lie derivatives, but different ones. They are not the same compared to what I had before, because I want this, instead of perturbing a Jordan curve, this time I want to perturb a homeomorphism indexed by real analytic vectors. So this is a bit vague, but I hope that I kind of convey what this type of integration by parts formula means with the previous one. So the theorem with Guillaume is existence and uniqueness of such measures. And relation to SL. And if you know the relation to SL is not too complicated, you take a Jordan curve that is sampled from your SL loop measure. You look at its associated welding homomorphism. This gives me a measure on the space of homomorphism, and I simply need to reweight slightly this measure, and I get a unitarizing measure. Okay. And for instance, this type of results are very useful because again they describe your SLE in a different way, and they give you one nice application of these results is, for instance, it allows you to cut random surfaces using an SLE on top of it into independent random surfaces. So, for instance, you pick a sphere, the random surface that has the topology of the sphere. You draw an SLE loop on top of it, and then the sphere is naturally split into two disks. And you can use these type of results to show that these two disks are independent, nice random surfaces with the topology of the disk.
So what's the difference between the two? It looks like the same.
So, because for instance, they are not the same operators. That's what I wanted to emphasize here. So you could write a different letter if you want.
So this one is not this one for a special V, which
no. Because so it's what I said there is if I want if you want, yeah, you can look at this picture here. The operator I had there was simply I'm modifying slightly my curve on the right hand side of the picture here with the flow that is defined. Whereas this one modifies the homomorphism that lives on the left hand side of the picture. So they are not the same. And this was also a source, I think, of confusion in.
There is a relation or not really?
Yeah, there is a relation, but which is not trivial. You have to do a change of variable basically. Okay. Thank you very much.
You have questions? Yes.
Since you mentioned the Ising model in the motivation, do you also have? Can you also see somehow this loop measure in the Ising model?
Yeah, so this I'm not so sure. I'm not sure what's the answer. I believe that you should be able to do that. You know, for instance, you can see CLE in the Ising model, and the SLE loop measure, I can derive it out of CLE. So
let me phrase it differently. Can you relate a loop measure to the CLE?
Yeah, so this yes. But and this has been done by Shinsu and co-authors. You have a precise relationship between CLE and SLE loop measure. The short answer is that SLE is the counting measure of CLE.
So the conjecture by the AM is 1 CL 125 is the unitary measure. Do you know what happens for other C? Did they have some conjecture for other C?
I don't know if they had a conjecture for other C now.
In their setting, it corresponds to CL 125.
Yes. No, okay, and I didn't say that the relationship between the two is so CL is 26 CM. I mean, in our setting, we also have, but I don't know if they say anything special about the values of CM.
Any more questions? Okay, so maybe we can thank Antoine again. I think we have no more talk for today. Tomorrow we start at 10, I think. Free time for
Are you going to